Hello, everyone, and welcome to Relations Lesson 2. We are looking at relationships between two quantities. I'm going to try to move through this one quick because Lesson 1 took a little bit longer than I was hoping. So let's try to get moving here. So it says, much of mathematics involves the search for patterns and relationships between sets of data. Many real-life applications of math investigate the relationship between two quantities. So we're going to start seeing a lot of this throughout the rest of the course. And basically through the rest of Pre-Calc 11 and Pre-Calc 12. So a couple of examples we have are the value of a computer is related to its age. So those are two quantities, right? Value and age. The price of a watermelon is related to its weight. So the values there, or the quantities, are the price and the weight. And the time taken for a person to walk to school is related to the distance they have to walk. So time and distance are related. And time and distance are a big one in physics, but hopefully you see that when you get in there. So a comparison between two sets of elements, or two different quantities, is called a relation. We are going to be looking at representing relationships between two quantities in several different ways. So we can do it in words. We can use a table of values. We can use a set of ordered pairs. We can use an arrow diagram, an equation. We've seen some of these already, a graph, and in our next unit, we are going to be looking at function notation. So it says here, investigating a relation. So it says here, consider the following relation. The cost, C, in cents per kilometer, of driving a car is related to speed, kilometers an hour, at which it's driven. So we know the cost of driving a car is related to the speed. Certain cars at certain speeds will use more gas, is essentially what they're looking at. So if you're driving on the highway at 120 kilometers an hour, you're going to burn a lot more gas than if you're sitting at about 100. So here we go. It says, the example illustrates a relationship between two variables, C and S. So usually we will see those quantities written as variables. And then we will have one dependent variable and one independent variable. And this becomes really important in science, especially. So in this case, the cost depends on the speed, right? The speed doesn't depend on the cost at all. The speed can be whatever it wants. But the cost, like how much it costs to run your car, is going to be dependent on the speed. So in this case, C is the dependent variable and S is the independent variable. So most of the time, our independent variable becomes the input and the dependent variable becomes the output. So we will have to find some input values and output values in order to graph or show this relationship with numbers. Don't worry about this. We'll get to that, I think, in lesson 4 or something. So let's look at that relationship, cost and speed. So it says here, obviously we would not attempt to collect data for every possible input value. We know speed is our input. It would just take way too long. So we can just choose some that make sense, right? So 20 kilometers an hour, 30 kilometers an hour, 40, so on and so forth, up to 120. And then what we can do is plug them into the equation that relates these two and find an output. And you can see we represent this relation in, first of all, a table of values. So when we have a table of values, our input, or independent variable, goes on the left, and the output, or the dependent variable, goes on the right. So you can see here, if you drive your car 20 kilometers an hour, it's going to cost you 10 cents a liter. I think that's what it was. 10 cents a kilometer, sorry. Cents per kilometer, yeah. C was represented as cents per kilometer. So it's going to cost you 10 cents a kilometer. If you were to drive at 70 kilometers an hour, it's going to cost you 7.5 cents per kilometer. So a lot lower. And then you can see as you speed up, it gets lower and lower, and then it comes back up to 10 at the end. So there's kind of a sweet spot there. Ordered pairs is another one. So it's very similar to the table of values, but instead of separating it, they're putting the pairs together, these pairs here. So we have speed on the left, which is the independent, and cost on the right, which is the dependent. And we're just grouping them in pairs rather than in a table. We can do a graph. We've already looked at graphs before. You can see this graph here. We always do the dependent variable on the y-axis or the vertical. Always do dependent, and then the independent on the x-axis. Always. And then you can see our points. We go lower, find that sweet spot, and then it gets more expensive as we speed up. A mapping diagram or arrow diagram is kind of similar to the table, but it's kind of showing it a little bit different, right? So we know 20 will, if we drive at 20 kilometers an hour, it'll cost us 10 cents a liter, 10 cents a kilometer, sorry. So you're drawing arrows from the input to the output. So those are just 4 different ways to represent that relationship. They each tell you all the information you need to know. So I'm just going to skip this page. And then we are going to talk about independent and dependent variables in a relation. So we've already talked a little bit about all of this here. I'll go over it briefly. So in an ordered pair, the values of the first coordinate are those of the independent, and the values of the second coordinate are the dependent. So in a ordered pair, we go independent, dependent. In a table of values, we go independent and then dependent. And that will be x and y. In a mapping diagram, we go independent to dependent, or I guess in this case it was S to C. On a graph, the independent variable is on the horizontal axis or the x-axis, and the dependent variable is on the vertical axis or the y-axis. And then we've seen all of that on the last page, but in an equation, this is where it's a little bit new, or we haven't seen an example, is we try to isolate the dependent variable. That means we try to get it by itself. So here's an example where we use y's and x's. So y is the dependent variable, and it's by itself. We have an equation y equals a bunch of stuff. And then the independent variable is x, and that's in the equation of a bunch of stuff. So you can think about that as our inputs, right? So if we put a value of x in, we can calculate a value of y. So you can put a value in there to find an output. You can put an input in and find the value of an output. Hopefully that makes sense. We're going to see a ton of equations in the future that look like that. Y is equal to 3x minus 5. That's a typical slope-intercept form equation. Dependent is equal to a bunch of numbers and the independent variable in an equation. Okay, consider the relation described by the equation. Y is equal to, oh, this is not in my, oh, they skipped the page. Did I not? Dang, I don't think I copied a page. That's okay, we'll go over that in class for sure. Consider the relation described by the equation y is equal to 2x plus 5. So in this case, y is our dependent variable, and x is our independent, or input. So the table gives us all of the input values, and we have to come up with the output values and then write them as an ordered pair. So we know the formula is, or the equation is 2x minus 5 So we can write that with our x value being -2. So 2 multiplied by -2 is -4, minus 5 gives us -9. So that's the output. And we can write that as an ordered pair of -2, -9. We can do the same thing with this value of x. Y is equal to 2, -1, minus 5. 2 multiplied by -1 is -2, minus 5 is -7. Awesome. So we have -1, -7 as our ordered pair. We could do it with an x value of 0. 2 multiplied by 0 minus 5. 2 times 0 is 0. Subtract 5 is -5. So we can start to see a bit of a pattern here. 0, -5. We'll do one more. Y is equal to 2, where x is 1, minus 5. Our input is 1, and our output is 2 times 1 is 2, minus 5 is -3. And we have 1 and, -3. It's easy to miss a negative. So you can start to see that the output is going up by +2, so we go -5, -3, -1, +1, +3. The input's going up by 1s, 0, 1, 2, 3, 4. And most of the time when we're dealing with a linear relation, we'll get into that in the next unit. But we know that linear is anything x to the power of 1, right? X to the power of 2 is quadratic. X to the power of 1 is linear. So anytime we have a linear relation, our inputs will go up at the same by the same value, and our outputs will go up by the same value too. So something to keep in mind. 2, -1, 3, 1, 4, 3. Now we're going to plot these pairs. So the first one we have is -2, -9. So we know that we go to the -2 on the x. So we start at 0 and go -2, and then to -9. That gives us a point right there. And then we can go to -1, -7. So go to -2 in the x, and then I go down to -7 in the y. And then we can go to we go to 0. So 0 on the x doesn't move. Down to -5, 1, -3. So we go to x is +1, but we still go down in the y to -3. And then 2, -1. And it looks like we have our relation there. I did 3 and +1 and 4 and +3. We don't have any context for this equation, whether it's continuous or discrete. So what you can do is just draw your line. If you're not sure, draw your line. That's it says right here, connect the points on the grid and extend the line in both directions with arrows at both ends. Those arrows mean that this line goes forever in that direction and forever in that direction. The next question says, use the graph to determine the value of y when x is 6. So what we want to do is we want to go to x is 6, which is right here. And we're going to scroll up. It looks like I drew my line terribly. Let's just try to, I wonder if I can put a line in. Oh, that is a massive line. Let's erase that. Let's see here, we're learning. There we go. Oh no, what is happening? I just erased all of my points. No. Is there an undo button? Oh, this is going horribly wrong. Okay, we have 1 and 3. 1 and -3, so we need 0, -5. Oh, why am I stuck on eraser? That's the issue right here. There we go. Let's put a line in. Let's see if I can do this time. It's not perfect, but it's better than the one I drew. Okay, back to the question. I apologize for that. Use the graph to determine the value of y when x is 6. So we go to x is 6, and we can trace it up. And this line is a little bit off. I apologize. It should be crossing there at that point. Normally you would just go to the line, but my line is wrong. Bear with me. And we can see that x is, or y is 7. So we know y should be 7. And then it says, use the equation to determine the value of y when x is 6. So had we been doing this and we didn't know the answer, we would have said, we cross at y is 6, and then we could verify because we know at the start of the question we have y is equal to 2x minus 5. So when x is 6, we can plug that in. Y is equal to 2. We put our 6 there. Minus 5. 2 times 6 is 12. Minus 5, which is y is equal to 7. So this would have told us here that our line was incorrect, but I knew that because I had the answer key. Awesome. Use the write the value of y when x is 6 in the table of values. We already filled the table of values. I apologize, so we're going to skip that. Use the graph to determine the value of x when y is 3. Okay, so we go up to our graph, we find y is 3 right here, and we can move across and find the value of x, which is 4. X is 4. This relation is called a linear relation because the graph of the relation is a straight line. See? Line. Line. Straight line. Cool. That's it. Thanks for watching. Don't forget to like and subscribe. Lesson 3 on its way in half an hour.